This is the first module in a series of AABC technical training videos. This program covers testing fans and taking pitot tube traverses in rectangular duct. Air balance preparation. Before setting up the fan for testing and doing pitot tube traverses, the technician first reviews the job's contract documents. These documents include the mechanical and control drawings, project scope, equipment submittals, and job specifications. From these documents, the technician determines what tab data sheets are required and what tools and instruments are needed for the job. The contract documents provide much of the required preliminary information, and the technician will enter this information on the data sheets before going to the job to conduct the site inspection. After the initial review of the documents, the technician fills out the preliminary data sheets. It is essential that the tab data sheets are filled out correctly and legibly. After going over the data sheets and the other materials, the technician determines the most effective balancing procedure for the system, as well as identifying any potential problems that may affect the balancing or future operation of the system. Before going on the job, the technician selects the instruments needed and verifies that they meet the calibration procedures stated in the specifications or by the instrument manufacturer. Included with the test data sheets is a separate sheet to list the various instruments to be used on the job. Site inspection. At the job site, the tab technician inspects the building envelope, HVAC controls, air distribution system, and the HVAC equipment. The technician checks that the building's doors, windows, ceilings, partitions, etc. are installed and properly sealed, and that the building is otherwise architecturally complete and ready for air balancing. The controls, including automatic control dampers and fan volume controls, are also inspected to determine if they are complete and operational. The supply and return air distribution systems are inspected to determine if the ductwork is intact and installed according to the drawings and specifications. The ductwork must be free of debris with no inappropriate openings, such as end caps left off. The ductwork is also inspected to determine that there is an unobstructed path from the fan to each conditioned space and back to the fan. Additionally, the technician inspects all dampers, including fire and smoke dampers, to verify that they are installed, accessible, operational, and open. Terminal boxes, reheat coils, electrical reheat components, etc., are checked for installation, accessibility, and operation. Outlets are checked and counted that none are missing and all are installed as specified. While inspecting the supply and return duct systems, the technician identifies appropriate locations to take pitot tube traverses. Air handling unit inspection. At the air handling unit, the technician checks that the fan housings, plenums, flexible connections, etc. are installed according to the drawings and specifications and are properly sealed. Starting at the mixed air plenum, the technician inspects dampers, filters, and coils to determine if they are clean and properly installed. The drive components are next. The technician checks that sheaves are properly aligned and tight on their shafts. Belts are adjusted for correct tension. Belt guards are properly installed. Motors are wired and energized. Proper starter and overload protection are installed. Correct fuses are installed. Motors are properly secured on their frames. Fan and motor bearings have been lubricated. Fan wheels are aligned correctly with proper clearance between the wheel and the fan housing. Next, the technician records motor, fan, and air handling unit nameplate data. Information on the motor includes amperage and voltage, horsepower, phases, service factor, motor manufacturer, type, and model and serial numbers. Unit nameplate data includes manufacturer, model number and serial number. Fan data includes type, rotation, and speed. If during the site inspection deficiencies in the system are discovered, the technician will note them on the report form. Setting automatic temperature-controlled dampers. Proper damper position during tab work is critical. The technician needs to be familiar with the sequence of operation of all the dampers in the system. If large dampers are incorrectly closed on startup or while the fan is running, serious damage could be done to the ductwork, filters, plenums, and other system components. When practical, the technician will work with the control specialist to ensure that the automatic temperature control dampers are positioned properly for balancing. Measuring fan speed. Starting with the supply fan, the technician momentarily starts and stops or bumps the fan to check rotation. Some fans have rotation arrows on them, but the technician always inspects the fan wheel and its arrangement to verify correct rotation. If the fan is rotating backwards, the electrical connections must be reversed before continuing. With the fan turning in the proper direction, the technician listens and looks for any undue noise or vibration. If excessive noise or vibration is detected, the technician will immediately shut the fan off, determine the problem as best as possible, note the possible cause on the data sheet, and then report the findings to the appropriate responsible person. If there are no problems, the technician takes speed measurements on the fan using a tachometer. This is a handheld contact tachometer. Contact tachometers are used for measuring rotational speed when the shaft of the tested item is accessible. They are usually supplied with several rubber or metal tips for centering the instrument on the rotating shaft and to ensure proper contact without slippage. When using contact tachometers, the instrument shaft is held parallel to the rotating shaft to ensure an accurate reading. The tip is held tightly enough against the shaft to avoid slippage, but not so tight as to increase drag, which would cause an incorrect reading. The push button is pushed and the RPM read. When the shaft is not accessible or for other reasons, non-contact tachometers, such as strobe lights and phototachometers, can be used to measure rotational speeds. A strobe light measures RPM by flashing an electronically controlled light at the rotating object. When the electronic flash is synchronized with the speed of the rotating object, the object will appear to stand still. A piece of reflective tape is used with a phototachometer. The tachometer counts the number of reflections in a set time period and records the RPM. To ensure accuracy, the technician takes successive readings until 2 consecutive repeatable values are obtained. The technician records this as actual RPM on the appropriate forms and compares it with the specified RPM. If the reading is not within 10% of design, the drives may need to be changed to speed up or slow down the fan. Measuring rotational speed in revolutions per minute, or RPM, is generally a simple procedure, but fans and other rotating equipment can cause serious injury. To prevent accidents, avoid wearing loose-fitting clothing, jewelry, long hair, or gloves when working near rotating equipment. Lock out the motor disconnect switch to prevent the equipment from starting while it is being worked on. After the supply fan has been tested and adjusted, the technician sets up and tests and adjusts any return or exhaust fan that is related to or interlocked with the supply fan. Setting up all the associated fans will ensure that the complete system is operating and is ready to be tested, adjusted, and balanced. Measuring fan motor voltage and current. As a general rule, voltage readings should be taken as close to the motor as conditions permit. Voltage readings are most accurate if taken directly at the motor terminal box, because they reflect voltage losses caused by resistance in the wiring or bad connections. However, in practice, Readings are usually taken at the motor starter, disconnect switch, or motor control center because these are much safer locations to take readings, and the sacrifice in accuracy is generally very small. A portable handheld volt ammeter is used to take motor voltage and current measurements. The meter may be digital or analog. To take voltage readings, the technician attaches the lead wires to the meter. When reading voltage on a three-phase motor, the potential between each phase is measured. For consistency, the technician reads the phase-to-phase voltage from left to right. In other words, phase 1 to phase 2, usually designated as L1 to L2. Phase 1 to phase 3, L1 to L3. And phase 2 to phase 3, L2 to L3. Only one reading is required when measuring a single-phase circuit, and that reading is from L1 to L2. The technician records the readings as actual voltage on the appropriate forms and compares them with the specified data. Motor voltage is acceptable if the measured voltage is within plus or minus 10% of the motor nameplate voltage. If the voltage is not within this range, the technician will notify the electrical contractor about the voltage imbalance. Current, or amperage, is measured using a clamp-on ammeter. When reading current on a three-phase motor, all phases are measured. The technician opens the jaws of the meter and places them around each wire in succession. A good technique is to read from left to right. The technician will read each terminal wire, T1, T2, and T3. Only one reading is required when measuring a single-phase circuit, and that reading can be on either the hot wire or the neutral wire. The technician records the readings as actual amperage on the appropriate forms and compares them with the specified data. To be acceptable, the current measured on any phase should not exceed the motor nameplate amperage. If the current exceeds nameplate amperage, the technician will consult with the appropriate responsible person. Measuring unit static pressures. With the system operating, static pressure readings can be taken in the air handling unit. The technician selects a manometer, pitot tube, and connecting hoses to take the readings. Manometers and pitot tubes are precision instruments that should be handled with care to avoid damage. The pitot tube's impact and static pressure sensing holes should be kept clean and open. To measure static pressure, the technician drills 3/8-inch diameter holes into the unit. These holes are drilled in the unit at accessible points away from filters, coils, or any other component that would interfere with the insertion of the pitot tube. At the unit, the tab technician sets up the manometer. For a liquid-filled manometer, this will require leveling the instrument, opening both high and low ports, and adjusting the zero adjustment knob so that the bottom of the liquid or meniscus reads 0. Other than verifying calibration, installing or charging batteries, and turning on the meter, no setup is required for electronic manometers. Next, the technician connects one end of a piece of tubing to the static pressure connection on the pitot tube. If the static pressure is taken on the discharge side of the fan, the other end of the tubing is connected to the high or positive port on the manometer. If the static pressure reading is taken on the inlet side of the fan, the tubing from the static pressure connection of the pitot tube is connected to the low or negative port on the manometer. The technician inserts the pitot tube in the test hole and static pressure is read from the manometer. Notice the pitot tube is facing directly into the airstream. For this air handling unit, the technician takes static pressure readings across the filters and coils and readings entering and leaving the fan. Point A is in the mixed air plenum before the filters. Point B is leaving the filters and entering the cooling coil. Point C is leaving the cooling coil and entering the fan. Point D is leaving the fan. A negative static pressure reading at C and a positive static pressure reading at D will give the fan's total static pressure, or TSP. The tab technician records the actual static pressures on the appropriate data sheets and compares them with specified data. Pitot tube traverses. During the preliminary preparations, the technician selected tentative locations for the pitot tube traverses. Because traverse readings can be inaccurate in a turbulent airstream, the traverse should be taken at least 8 duct diameters downstream and 2 duct diameters upstream of elbows, transitions, takeoffs, dampers, or any other restriction or obstruction that can cause turbulence. In the field, the technician confirms these locations or selects new ones that fit the criteria for taking accurate traverses. If the duct configuration permits it, the technician will take pitot tube traverses and static pressures at the main supply duct, outside air duct, return air duct, and all branched duct locations. In order to make a pitot tube traverse, the technician first determines the number and spacing of the holes in the duct and the markings on the pitot tube. The number of holes drilled, their distance apart, and the number of pitot tube points are based on the criteria for a rectangular duct, that a minimum of 16 and a maximum of 64 readings will be taken at centers of equal areas. To determine the number of holes and distances to be drilled, the technician arbitrarily picks a number and divides it into the length of the side where the holes will be drilled. If the result of that division is greater than 6 inches, the technician will continue with larger numbers until the result is 6 inches or less. For example, in a duct that is 36 inches wide by 24 inches high, the technician decides to drill the traverse holes along the 36-inch side. To calculate where to drill the holes, the technician arbitrarily starts by dividing 4 into 36 inches. This gives 9-inch centers, which does not meet the criteria of 6 inches or less. Next, the technician arbitrarily decides to divide 6 into 36 inches. This gives 6-inch centers, which meets the criteria of the least number of holes to be drilled with centers not greater than 6 inches apart. So the number of holes to be drilled in the 36-inch side is 6 at 6-inch center. This is the second video in the AABC Testing and Balancing Technical Training Series, Balancing Single Zone Systems. Fan and system setup. In this video, you will learn basic air balancing procedures by going through the balance of a single-zone air conditioning system. Single zone is a control term meaning that there is only one thermostat in the conditioned space to control the heating or cooling for that space. To balance a single-zone system, the tab technician first reviews the prints, completes the preliminary data sheets, and sets up the fan and duct system for balancing as outlined in previous training videos. While still in the office, the technician selects tentative locations for pitot tube traverses in the main duct, return air duct, outside air duct, and all branch ducts. Then, during the site inspection, the technician confirms that these locations fit the criteria for taking an accurate traverse. If they do not, the technician selects new locations. After setting up the fan, the next step is to measure the system's total air. One way to get total airflow is to take a pitot tube traverse in the main duct. A second method is to traverse each of the duct branches and add the results. A third way to get total airflow is to traverse the return and outside air ducts and add the two totals together. A fourth method is to read all the outlets and add the readings together to determine total air. On most tab projects, the specifications call for balancing the system at plus or minus 10% of design. Another way of saying this is 90 to 110% of design. However, if the total air is greater than 20% above design, or in other words, 120% of design, the technician may decide to reduce the fan speed to bring the air volume down to 10 to 15% above design. If, however, the measured airflow is below design, the technician will increase the fan speed to bring the airflow as close to 110% of design as possible. The reason for increasing the air volume above design is that during the balancing process, there will be some loss of total air, generally between 5 and 10%. This loss is due to dampering. After total airflow has been measured, the technician uses the fan laws and drive equations, which will be discussed in later videos, to calculate the needed adjustments to the fan and motor sheaves to increase or decrease fan speed. For example, because air volume and fan speed are directly proportional, in order to reduce the air volume by 10%, the fan speed will need to be reduced by 10%. Branch balancing. The tab technician has now verified that all HVAC components are operating satisfactorily and has tested the system and determined that it has the proper airflow and pressures available to continue the balancing. Next, the technician will begin testing and balancing the airflow at all the branches. To do the balancing, the technician will measure the airflow in each of the branches to determine which branches are over-designed CFM and which are under-designed CFM. If any branch is especially low, the technician will investigate, looking for blockages or excessive friction and dynamic losses in the duct. The cause of the low airflow may be determined by inspection or by taking a static pressure profile of the branch in question. A manometer and static tip or pitot tube is used to take static pressures. When taking a static pressure profile of a branch duct, the technician takes the first reading at the takeoff from the main and progresses along the duct until evidence of a blockage or resistance is found. In this branch duct, the static pressure is 1.98 inches of water gauge as the duct goes into the wall, but only 0.52 inches where the duct comes out of the wall. It is obvious that the cause of the 1.46-inch drop is located in the duct as it passes through the wall. Probably a fire damper is closed. The technician opens this fire damper access door and finds the fusible link on the fire damper has come loose, and the damper is partially closed. After all investigations are complete, the technician starts the branch balancing at the branch with the highest CFM and adjusts that branch damper until the airflow is within 10% of design. This datasheet shows outlets S1, S2, and S3 on this branch. As you can see, the design for each outlet is 200 CFM, and therefore, the design total for this branch is 600 CFM. The technician is going to take a pitot tube traverse in this branch just after the branch damper. 2 test holes will be drilled in this 10-inch diameter duct. Remember, in rectangular ducts, a number of holes are drilled based on the size of the duct. But in round ducts, only 2 test holes are needed. However, they must be located 90 degrees apart. In order to do the traverse, the technician marks the pitot tube with an erasable marker at 10 locations. The marks are based on the radius of the duct and a constant for each test point. The pitot tube is marked so that the technician can take 20 velocity pressure readings in the duct, 10 for each hole, at centers of equal concentric circles. To determine where to mark the pitot tube, the technician divides the diameter of the duct by 2 to get the radius, and then multiplies the constant for each traverse point by the radius. For points 1 through 5, the resultant number is subtracted from the radius. For points 6 through 10, the number is added to the radius. As you can see, the first mark on the pitot tube, starting from the top of the pitot tube, is 1/4 inch. The 5th mark is 3 1/2 inches. The 6th, 6 1/2 inches, and the 10th, 9 3/4 inches. For the first mark, the constant .949 is multiplied by the radius of 5 inches. The result is 4.75 inches. The 4.75 inches is then subtracted from the 5-inch radius, leaving 0.25 inches or 1/4 inch. For the fifth mark, the constant .316 is multiplied by the radius of 5 inches. The result is 1.58 inches. The 1.58 inches is then subtracted from the 5-inch radius, leaving 3.42 inches or 3½ inches. For the sixth mark, the constant .316 is multiplied by the radius of 5 inches. The result is 1.58 inches. The 1.58 inches is then added to the 5-inch radius, giving 6.58 inches or 6½ inches. For the 10th mark, the constant .949 is multiplied by the radius of 5 inches. The result is 4.75 inches. The 4.75 inches is then added to the 5-inch radius, giving 9.75 inches or 9¾ inches. To check the rounded off calculations, the technician adds the first and 10th numbers, second and 9th, third and 8th, fourth and 7th, and 5th and 6th. The sum of each will be the diameter of the duct. For example, add the first mark plus the 10th mark, 1/4 inch plus 9¾ inches equals 10 inches. Looking at the duct traverse datasheet for this branch shows the design duct size, area, FPM, and CFM. The area of the duct is found by multiplying 3.1416 or pi times the radius squared divided by 144 square inches per square foot. The area is 0.545 square feet. The design volume is 600 CFM. The design velocity V is found by dividing the volume Q by the area A. The design velocity is 1100 FPM. The technician took a total of 20 readings, 10 in each test hole. The datasheet shows the results of the 20-point traverse reading. The average velocity is 1,303 feet per minute, and the volume measured is 710 cubic feet per minute. To balance this branch, the technician closes the branch damper until the total of the 3 outlets reads 660 CFM, 110% of design. The technician continues in this manner, traversing all the branches, cutting the high branches and reading the low branches, making 1 or more passes until an acceptable balance is attained. Terminal balancing. After all the branches are adjusted to within 10% of desired airflow, the technician proceeds with balancing the outlets. The technician begins by measuring flow at the outlet nearest the supply fan, and then reduces any excessive flow by dampering at the takeoff to bring the airflow within 10% of desired flow. Then the technician moves to the next outlet on the same branch and adjusts that outlet's takeoff damper as needed. The technician continues balancing outward by branches until all the outlets have been adjusted, making 1 or more passes until an acceptable balance is obtained. The experienced technician will not use the outlet or inlet device's face volume damper to reduce airflow. Using a register's or ceiling diffuser's face volume dampers to reduce airflow can result in excessive noise, poor air distribution, and an improper balance. From the datasheets, you can see that this branch has been adjusted at the branch damper to 660 CFM, which is 110% of design. The readings with the capture hood indicate that outlet S1 is 260 CFM, S2 is 230 CFM, and S3 is 170 CFM, for a total of 660 CFM. To balance these outlets, the technician cuts the damper to outlet S1 to supply 210 CFM and then reads outlets S2 and S3. The outlet S2 now reads 250 CFM, and the outlet S3 reads 190 CFM. Next, outlet S2 is dampered to 220 CFM. Outlet S3 is read, and it is 210 CFM. S1 is checked, and it has remained at 210 CFM. The technician now has all the outlets on this branch balanced to within 10% of each other. The branch now has a total airflow of 640 CFM, or 107% of design. The technician now goes to the next branch. The outlets now read a total of 650. The design is 600 CFM. Therefore, this branch was adjusted to 108% of design during the branch balancing phase. The balancing then continues with outlets S4, S5, and S6. After all the outlets in the system have been adjusted, it still may be necessary to make slight adjustments at the branch dampers in order to achieve the total system balance. As all the outlets have been balanced to each other by branch, an adjustment at the branch damper will increase or decrease all outlets on that branch proportionally. Final balancing. After the supply and return air terminals are balanced according to specifications, the technician goes back to the fan unit to set the required minimum outside air and record the final system data. To set minimum outside air, the technician first must determine the actual amount of outside air. One way to do this is with a pitot tube traverse of the outside air duct. Another method is to subtract the actual return air CFM from the actual supply air CFM. Supply air, of course, is equal to the return air plus outside air. However, if neither of these methods is satisfactory, the temperature method may be used where practical. With this method, the technician uses a digital thermometer to take an air temperature reading in the outside air duct and one in the return air duct close to the unit. Then the technician takes a temperature reading in the mixed air plenum. Depending on the size of the mixed air plenum and the practicality of taking readings, the technician may elect to do a traverse in the mixed air plenum by measuring air temperatures at the center of each filter. By adding the temperature readings at the filters and dividing by the number of readings, the technician determines the average mixed air temperature in the plenum. To determine percent of outside air, the technician will take the three temperature readings, outside air, return air, and mixed air, and plug them into this equation. Percent of outside air equals temperature of the return air minus temperature of the mixed air divided by temperature of the return air minus temperature of the outside air times 100. The temperature readings for this unit are 75 degrees return air, 78 degrees mixed air, and 95 degrees outside air. By calculation, the amount of outside air is 15%. However, the design is for 20% outside air. So the technician must now reset the outside dampers to bring in the correct amount of minimum outside air. To calculate mixed air temperature, the technician will use this equation. Temperature of the mixed air equals percent of outside air times temperature of the outside air plus percent of the return air times temperature of the return air. Since the required amount of outside air is 20%, the amount of return air is 80%. Therefore, to obtain the correct amount of outside air, the technician will adjust the outside air dampers until an average mixed air temperature of 79 degrees is measured in the mixed air plenum or at the filters. The first two methods to set outside air, pitot tube traverse of the outside air duct or subtracting the actual return air CFM from the actual supply air CFM are preferred over the temperature method because temperature readings generally are both difficult to take accurately and are time-consuming. However, if the temperature method is used, it is best to set the dampers when the temperature difference between the outside air and return air is at least 20 degrees. After the outside air damper has been